Can you hear me? Please let me know. Okay. Can you hear me well? Right. I'm running. That should work. Okay, I won't wait for 2 minutes until people join. This is the last webinar of this year, and it's a bit quiet. Should be fine. How about now? How about now? Okay, should be now. Should be good. So yes, this is the final webinar. We will continue webinars in September when the year 13 assignments are out. So if you are in year 12 and you've completed most of the assignments, you automatically progress to year 13. Okay. Right. So we can start. We have it's 6 o'clock. So if you have any burning questions right away, I'm happy to answer. If you have any questions related to electrostatics or combinatorics, happy to answer. I was just saying that it's the final webinar, just in case, and go for a summer break after today. If there are no questions, I have some questions prepared for you, of course, as usual. So I'll share my screen. Make sure the chat is here. Good. Right, find the electric field at a point X. At a point X, the string is uniformly charged with charge density per unit length rho. Charge density per unit length rho. So what does that, well, what does it mean? Charge density per unit length. That means that the total charge, the total charge on the string. So let's say the string is positively charged. So the charge divided by the length of the string is rho. That's what it means. The charge density per unit length. That means a unit length of the wire has charge rho. Cool. And we can find the charge by multiplying the length times rho. So this might be useful. The total charge is rho times the length. Okay. Now to find the electric field, we know that the electric field from a point charge is Q divided by 4 pi epsilon naught r squared. So if you want to find the electric field at point X, you find the electric field. Oh, obviously it's going to be to the right. Here, E is question mark. But you don't have a single charge. You have a charge uniformly distributed along the wire. So you need to find the field from this charge, field from this charge, the field from this charge. Well, you can say that they're separate charges. So that's quite tedious, doing every single charge. So let's say we take a charge. So we take a piece of wire of length dr. This is the length of that small piece of wire. The charge of that piece of wire, Q, is going to be rho dr. Of course, so if the length is dr, charge is rho times length, so it's rho times dr. So that's the charge of this little bit. The electric field produced by that small charge, let's call it dE. dE is the charge, so charge of the small charge of the segment of length dr. The electric field produced by that segment is the charge divided by 4 pi epsilon naught r squared, where r is the distance from X to that small segment. So this is R. Okay. And now what we need to do is sum all of these small segments. So sum up of, well, we're using the principle of superposition. We're using the principle of superposition. We're saying that E is the sum of E's. Okay. Sum of E's from each individual segment. Does that make sense? Sum of EI. Sum of all this. So the total electric field is the sum, is the vector sum of all fields. But because they're all in the same direction, it's just the sum. It's the sum of each. So, and we know that the sum, as when you make the sections very, very small, the sum becomes the integral. Q. All right. So you know what? I'm going to continue here. I know the Q is rho dr. It's going to be rho dr over 4 pi epsilon naught r squared. And we can write that. So dE, I just copy this. dE is rho dr over 4 pi epsilon naught r squared. And this is beautiful because we can integrate right away. Integrate both sides. Now E, well, let's say we start from here. We start from here and we go left all the way across the rope. So we take this section first. So E goes from 0 because if you consider 0 length of the wire, it's 0 E up to E, which is what we're looking for. E is the total. You can call it E total, but okay, let's sound it E total. ET. And this changes from the length of the wire well, you go from x to x plus L. You go from x to x plus L. Okay. So why I go from right to left? Because I go in the increasing direction of R. I make sure that dr is increasing as I go from right to left, and it is. Because if I went from left to right, I would have to put a minus here, and that would be confusing. So the reason why I'm going from right to left is I'm going in the increasing direction of R, in the direction that R increases. Anyways, this is quite a simple integral. So I take all the constants out as I normally do. So rho is a constant, 4 pi epsilon naught is a constant, and I'm left with dr over r squared between limits x and x plus L. Okay, so who can integrate that for me, please? Who can integrate that for me? -1 over r, correct. Thank you, Andre. -1 over r between limits x and x plus L. And we are left with rho 4 pi epsilon naught. So yeah, -1 over x plus L plus 1 over x. And of course, on the left-hand side, it's from 0 to ET, and that's a very easy integral, so they're just ET. And so ET, E total is, so what's that going to be? That's rho 4 pi epsilon naught, 1 over x minus this. So we multiply this by x plus L. So x plus L minus x over x plus L. X cancels, and we're left with rho L 4 pi epsilon naught x plus L. And that's the answer. Okay, the total field at that point is this. Right. Problem 2. What is the electric flux through the curved surface of the truncated cone? So it's unmentioned here, but the electric field is constant. So the electric field goes like this. Hope that makes sense. Electric field goes like this, and it's uniform. Okay. And the electric flux, how well do you understand what electric flux is on a scale of 0 to 10? So 0, I don't understand at all, and 10, I fully understand what electric flux is. Okay. All right. So I better explain what electric flux is. Have you heard of magnetic flux? Yes or no? Magnetic flux. Okay, so you have heard of magnetic flux. Well, the electric flux is the same thing. There's no difference. I mean, it's just this is the magnetic field and the electric field, right? So if you imagine an electric field, so an electric field, it's like these are lines of the electric field, and you imagine a surface. Imagine a surface. The surface of area A, and the electric field is E. We can simplify in saying this is a uniform electric field. That means lines are parallel. An area is a flat area perpendicular to the field. So the flux is the sort of the amount of electric field caught by this surface. Is how much field goes through the surface. And the flux is defined as E times A. Okay. So it's just E times A. Now, technically, it's a dot product. Yeah, it's a dot product. But you would argue, how could it be dot product? E is a vector, yes, but A is not a vector. Or is it? Well, area can be a vector. Okay, so it is a vector, area, and the direction, the size, the vector A is defined as follows. So the modulus of A is the area, and the direction of A Do you know a clever way how to write a direction of a vector? It's A divided by modulus A. This is, well, it's a unit vector. Oh, you could do that. Direction of A. Direction of A is normal to the surface. But you can say there are two directions which are normal to the surface. Yes, true. You can have up or down, and it's a matter of choice. Yeah, just like in usually in physics, you have a choice of direction, and it depends. Depends on how you look at it, right? So yeah, or you could say that the flux is the electric field multiplied by A multiplied by the cosine between the electric field and the normal to the surface, cos theta. Normal to the surface. So yeah, so two equivalent definitions. Basically, you can think of it as how many, so flux is how many lines actually pass through the surface. It's just like, you can think of flux of water. Let's say you, on a rainy day, you go outside, and flux is how much rain you can actually catch with a surface. And this depends on three things. Now, it depends on the area, of course. The bigger area, the more rain you catch. The strength of the rain, so the field, E. This is, so the stronger the field, the more rain you will catch. And of course, the angle, because if you put the surface vertically, you won't catch much, or you won't catch much rain. Yeah, but you won't catch much water. So you want the surface to be at 0 degrees. That means the normal is 0 degrees to the rain. So if you put it, the surface parallel to the rain. Now, when I say surface is parallel to the rain, I mean the normal is parallel to the rain, then you'd catch the most rain as possible. So do you think you have a better understanding on flux now? Okay. So the question is, what is the electric flux through the curved surface? Now, we know that the flux is the field times the area, and that, well, that's certainly not easy, because, well, it's the integral. It's the integral of E of d by dA. So you take every little surface here, you add it all up, and that seems like an impossible task, and probably is close to, well, it's okay, it's not impossible, but it's really hard. So is there a way out of it? Well, there is, in fact, Gauss's law. Gauss's law says that the total flux through a curved, through a closed surface, total flux through a closed surface is equal to the charge, charge located inside that surface, and just a second, so that I don't embarrass myself, I forgot the multiplier. Okay, that's easy. So it's the charge that is located inside the surface divided by epsilon naught. In this case, how much charge is enclosed in that truncated cone? How much charge is enclosed in that cone? It's not a trick, not a calculation question. Well, the field is uniform. What does that tell you? The field is external. This is what you need to know. The field is external and it's uniform. So how much charge is inside the cone? Inside the truncated cone. Okay, what would if you had a charge inside the cone, you would see field going, the charge would produce a field, and the charge produces a field in an outwards direction. It is no charge, because if there was a charge, the field wouldn't be uniform. Unless it's a very elaborate system where somehow the charge has a distribution. No, is it? Well, it's not said. Nobody says that there is a charge, and besides, it's a uniform field which is external, and the cone doesn't affect the field in any way. So yes, there's no charge there. There's no charge in the field, so this is 0. So the total flux through the surface of the cone is 0. Now we just add up all the fluxes. So we have the flux going through the small circle, the flux going through the small circle, plus the flux going through the large circle, big, plus the flux going through the curved section. And we know that this has to be 0. Okay. Now we choose a vector. Now we usually choose a vector going inside. So here we choose a vector like this. Here we choose a vector going like this, so into or out of. So internal normal and external normal. So this is the vector area vector. So this is A1 vector, and this is A2 vector. And the angle is alpha. All right. So the small flux is E times A1 multiplied by cosine of the cosine alpha, plus for the big circle, it's the flux, the magnetic field, electric field, times A2 times cosine. Now the angle is this. It's not alpha anymore. It's pi minus alpha. Pi minus alpha, because we're choosing the direction. Well, you can understand it on an intuitive level, actually. So through one of the surfaces, through one of the circle, it comes in, and through one of the circles, it comes out. So one is going to be positive, one is going to be negative. So it can't be cos alpha. So, and one of the reasons is that the normal vector is internal and not external. So it's a matter of choice. It doesn't matter which way you go about it. Plus so, and cosine pi minus alpha is minus cos alpha. So phi curved is EA2 cos alpha minus EA1 cos alpha. Yeah, so do you all see how I did this? Math-wise, this is just mathematics. This is minus, so I took that to the other side. It became positive. This became negative. Okay, and A2, we know that. So phi curved. We know that so A2, we know that it is pi r squared cos alpha minus E pi r small squared cos alpha, and just make it pretty. E pi cos alpha, open bracket, r squared minus r squared. That's it. That's the flux through the curved surface. So how much flux in total passes through the curved surface? So some of it comes in, some of it comes out. And obviously the difference between what comes in and what comes out is equal to the difference in the flux passing through the big circle and small circle. Now, if you read the assignment carefully, you would know that if you have an infinite flat charged plane, so if you have a flat plane like this, and it's charged, and it's infinitely large, then the electric field is going to be Q, oh, sorry, sigma, ooh, sigma divided by 2 epsilon naught. Oh yeah, that makes perfect sense. Yes, that was minute of madness. Yeah, so sigma is the surface charge density. Sigma. So sigma is the charge per unit area. Now, of course, if it's an infinite plane, it's going to have infinite area. But we're talking about so how does that make sense? I mean, it's like that joke about the spherical horse in a vacuum. Have you heard about the spherical horse in a vacuum? A physicist was asked to design a model that predicts the outcome of horse races. Yeah, so in order to make a lot of money, if you can predict the outcome of a horse race, you can earn a lot of money on betting on the horses. And the physicist, yeah, said, I have a model, but it only works for a spherical horse in a vacuum. And the same here. Like, how is that relevant? If it's an infinite plane. Well, this formula works as long as the dimensions, so the length and width of the plane, are much larger than the distance to that plane. So if this is the width of the plane, and this is the length of the plane, and this is d, the distance to the plane, we say that width is many times larger than d, and L is also many times larger than d. So basically, it's a plane which is large compared to the distance, right? So obviously it is not infinite, but this formula works really nicely with planes which are reasonably large. and you're reasonably close to them. So yeah, and do you notice anything special about this? Do you notice anything special about this formula? Anything surprising? The electric field is sigma divided by 2 epsilon 0. What is not there when, well, there's no pi, yes, but electric field is flux times the area, no, flux divided by area, so an area contains pi, so there's no d, yes. There's no, this doesn't depend on the distance. Look at that. Yes, we just said as long as d is small, this is true, but it doesn't contain d. So basically, if you move up, the electric field doesn't change. Well, that means it's a uniform field, doesn't it? This just says that the field is uniform. Field is uniform because it doesn't change with. That's how uniform fields work. They don't change with the distance. And yet again, it's only accurate for an infinite or a very large plane. Cool. And now we are talking about an infinitely charged slab of thickness h. So this is a simplified version of the question from the assignment. So one of the final ones, one of the more difficult ones. An infinitely charged slab of thickness h and volume, infinitely charged slab of thickness h and volume charge density rho is placed horizontally. Find the electric field as a function of z. Okay. So let's consider a very thin slab here. And we know that, so this is a cross-section view. I hope you understand that. So this is something like this. The slab is infinite, like this, like this, like this. Yeah, so it's a, and this is the cross-sectional view. This is a view from the side. This is the side view. And so we take a small piece, so a small slice, a very thin. We take a very thin slice of width d or dz. Why not dz? And the charge, the total charge of that slab of the slice of the slab is the volume times rho times the volume charge density, and the volume is area times dz times rho. Why did I call it dz? That's ridiculous. dh, which would be much better. dh. Okay. And the electric field produced by that slab, electric field at this point, and is the surface charge density surface charge density of that slice divided by 2 epsilon naught. And the surface charge density, as we already discussed, is the charge divided by area. So area cancels out, doesn't it? So we have sigma is Q slice divided by area of the slice. So it's going to be dH times rho. So in other words, this is going to be rho times dH over 2 epsilon naught. The electric field produced by this thin slice. And if we cut it into slices, and label them slice 1, slice 2, slice 3, slice 4, etc. The total field when, so this is Z and this is H. So when Z is greater than H, that means we are above the plane. So when we're above the plane, the total field is E1 plus E2 plus E3 plus etc. plus En. How many? Yeah. So, and of each slice, it's this. It's rho dH1 divided by 2 epsilon naught plus rho dH2 divided by 2 epsilon naught plus etc. But if we take out rho divided by 2 epsilon naught, all we have is dH1 plus dH2 plus etc. plus dhn, which is in fact just H. Because if you add all the H's, all the DH's, so this is DH1, DH2, so it's going to be rho H over 2 epsilon naught. Okay, so this is what happens when you're above the slab. If you're below the slab, it's the same thing, it's just going to be down. So here at point A, let's call it at point A. At point B, EB, it's going to be the same thing, but down. So it's going to be minus rho H divided by 2 epsilon naught. Now, let's say you are at the point C, and let's say you are at distance x away from 0. So EC. So below you, you have a slab of thickness x. So it would be the field from the slab below, which pushes you up. If you're a positive charge, it pushes you up. And the part of the slab above you pushes you down because it's positively charged, so it pushes you down. So minus the electric field produced by the piece of slab above you. And we already have the formula. It's rho H. Yeah, so it's the slab below you has thickness x. So it's rho x divided by 2 epsilon naught minus the piece of slab above you. What's the thickness of the slab above you? Let's test your attention. What's the thickness of the slab above you? If you're at point C, H minus X, very good. So it's going to be rho H minus X over 2 epsilon naught. So it's going to be rho 2 epsilon naught 2x minus H. And that's when you are inside. Okay, and then you can draw a graph. So this is very, very similar to one of the questions in the assignment. It's one of the optional questions, but sure you can give it a go. So here is the z-axis, and this is the field, and up is positive, down is negative. So at point 0, at 0, we know the field is minus rho h divided by 2 epsilon naught, and it goes like this. Okay, now we know that when you are h above, so let's say this is h above, the field is going to be this much, which is rho h divided by 2 epsilon naught, and it's going to be constant because it does not change with distance from the slab. And then in between, it's just going to be linear. And surprise, surprise, when it is h over 2, when you're halfway in between, the field is 0, which makes perfect sense, right? Because if you're right in the middle, there's no field whatsoever because the two fields cancel out. And this is the electric field as a function of z. Now, if you want to be clever, you can write it out as a piecewise function. It would be electric field of z is equal to. No, this is a very good practice. So I advise you to give it a go like this. For some, it would be super easy. For some, just have a think about how would you write EZ. Now, this is the graph. How would you write it as a function? Yeah? And I've given you a structure how you can do that. Okay, so now just let's look at some of the questions from the actual assignment. So the first one, 3 positive charges connected by 2 strings. Find the tension in each string. So here you kind of need to use the you need to find the tension in each string. So you look at Q1. Q1 has the tension force T1. So this is Q1. And there are positive charges. So this is F2 and F3. So, and you would say that F3 plus F2 equals T1. But this is not what I wanted to discuss with you. The question what I want to ask you is, why can we do it? Why can we write that they are balanced? How do we know that all these forces balance each other out and the system is stationary? Maybe a silly question, but could it be that the system is not stationary, that it's accelerating? Mass. Oh, yeah, mass doesn't matter. Well, I mean, it would matter if you had acceleration. They are stationary. The question is, how do we know that they're definitely stationary? The center of mass is a fixed point. True. The center of mass is, well, yeah. Center of mass is not moving. True. Could it? There's so many forces. How do we know that F2 and F3 are balanced by T1? Honestly, it's not a very difficult question. And Vanessa, you're thinking in the right way. Oh, I believe that's Ben, right? If I'm correct. Oh, well, we know they're stationary because they are internal forces. Like all of these, if you look at the system, like F2, F1, F3, F2, T1, they're all internal forces. What does that mean that they're internal forces? It means every force has a pair. Like T1 has minus T1 somewhere because it's according to Newton's third law. So it's going to be T1, T2, sorry, T1, T1, T2, T2, and this is going to be F2, F3, and this is going to be F1, F3, and this is going to be, oh, the wrong way. It's going to be F1, F2. And when you come to adding all of these forces, like if you add all of these forces on the system, you would see that, yeah, because if this mass is being pushed by this mass, sorry, this is not F1, this is F2. This is the same force as this one. And this F3 is not the same. Oh, it's embarrassing. Let's relabel them. So this is force F1 being pushed by 2. This is 1 being pushed by 3. This is 2 being pushed by 3, and this is 2 being pushed by 1. This is 3 being pushed by 1, and this is 3 being pushed by 2. Right. And if we add all of these forces, total force, so the acceleration of the system, mass times acceleration of the system, is the total force. And the total force is F12 plus F13 plus T1. Then, well, you know what? No, I will consider the direction as well. So it's going to be minus F12 minus F13 plus T1 minus T1 plus T2 minus F23 plus F21 minus T2 plus F31 plus F32. And you can see that T1 cancels, T2 cancels, 2, 3, 2, 1 cancels with 1, 2, 1, 3 cancels with 3, 1, 2, 3 cancels with 3, 2, and the total force is 0. So the acceleration of the system is 0. Right. So this is just small thing that came into my mind when I was looking at this problem. Just wanted to mention that. I don't know if you find this useful. And the rest is just doing 3. This is not. I'm not solving the problem. Yeah, I'm just pointing something out here. So I hope that makes sense. An inf. Oh, I wanted. That's not what I wanted to do. I want to do the sphere. I wanted to do question 9. Spherical ball of radius r has charge q uniformly distributed over its volume. Find the electric field created by the ball at the distance r away from the center. So last week, 2 weeks ago, we discussed, and this is covered in example 6 very thoroughly. So do look at example 6, that if you have a sphere and if you're outside the sphere, sorry, if you have a spherical shell, for a spherical shell, if you're outside the shell, the electric field is Q, the charge on the shell, divided by 4 pi epsilon naught r squared if r is greater than r, where r is the radius of the shell. And if the radius is less than r, if you're inside the spherical shell, the electric field is 0. Okay. Now here, we're not talking about a shell, we're talking about a spherical ball of radius r. So this is a spherical shell, and we're talking about a spherical ball. Now, if it's a conducting ball, it's a different situation, because if it's a conducting ball, all the charge will go to the surface, and it would be a shell. Yeah, because we don't care about what's inside the ball. If it has no charge, then it's no different from a shell. So it's a non-conducting ball. So when we say a ball is uniformly charged, it implies that it is not a conducting ball. Because a conducting ball, the charge would redistribute at the surface. It's a must. Okay. Well, if you're outside, well, there's no difference. There's no difference here, because you add all of these thin shells, and it turns out that outside is going to be Q divided by 4 pi epsilon naught r squared, where r is the distance from the center. So r, this is if r is greater than r. So this is not different from a single shell. You think about it, it's just many shells, like a charged ball is many shells put together. Now, what happens if you're inside? It's a more interesting situation. So let's So you can imagine that we split the ball into spheres. And let's say we are here. Now, if we are at point A, we are inside all of the spheres all of these shells that are further away from the center, but we are outside of all of these shells. Okay. Okay, does that make sense? So if we are at point A, we are inside all of these shells, but we are outside all of these shells. Does that make sense? Can you tell me? Does that make sense to you? Okay. So the electric field at point A would be just the field from the blue. Is the electric field from the inner shells. Okay, so we need to find the total charge of the so the charge of the inside divided by 4 pi epsilon naught r squared. Right. So because the charge is uniformly spread by volume, Q in is the volume of the inner sphere divided by the volume, the total volume, multiplied by the charge. So it's a fraction. It's a fraction of the charge. It's a fraction of the charge by volume. And the fraction is the inner volume divided by outer volume. So, and it's 4/3 pi r cubed divided by 4/3 pi r capital cubed multiplied by the charge. And we can substitute that into here. And so 4/3 pi cancel, and r cubed cancels with r squared. So it's going to be q r divided by 4 pi epsilon naught r cubed. Can somebody tell me the significance of this result? How would you describe the relationship? How would you describe the relationship in front of you? So the electric field, so if R is less than R, the electric field is Q R divided by 4 pi epsilon naught R cubed. So we're playing the spot the relationship game. It's a very important game for a physicist. You need to identify which are variables and which are constants. And once you isolate the constants, you would see that this is a relationship. What is the relationship? It is linear. Yes, very good. Because basically what we are saying is that the electric field is proportional to the distance from the center. The electric field is proportional to R. And this is super important because, well, It's interesting. It's interesting. And plot your answer as a function of R. Well, yeah, that's fairly straightforward now, because you have the electric field and this is R. So this is the radius of the sphere. It starts with here, you start here, then you go up. It's a linear relationship, and then it goes, and then it decreases. So here it's proportional to R, and then it's proportional to 1 over R squared as normal. So this is how it behaves. This is how the electric field behaves inside and outside the sphere. No, so once again, this is a uniformly charged ball. Yes, not a spherical shell. For a spherical shell, it's just going to be 0 and then like that. So for a spherical shell, it's just going to be like this. Good. And this brings us to problem 13. A spherical ball of radius r with charge plus q uniformly distributed over its volume is fixed with its center at the origin of an inertial reference frame. A narrow tunnel has been drilled from its north to south pole. A test negative charge minus q of mass m is dropped into the tunnel from the north pole. Calculate the position zt of the charge as a function of time. Wonder where the phrase North Pole comes from, but interesting. How do you define North Pole of a charged sphere? Anyways, we have a charged sphere with surface charge plus Q. And we have a tunnel from the North Pole to the South Pole, if that is a thing with spheres. This probably reminds you of something. We had a similar thing when we talked about what? Does anyone remember? Right. Let's introduce an axis. Simple harmonic motion. Yeah, absolutely. Well done. Well done, Edith. So this is the distance. This is x-axis downwards. So this is 0. This is minus r. And this is plus r. So I'm just introducing an x-axis. And let's say we are here. No, I've displaced, let's say we are here. Let's say the charge is at this point, a distance x away. Charge is at x. At x. Now it's a negative charge, so field at x is, and we already established that the field at x is going to be downwards because it's a positive charge. The field at x is E at x is q x divided by 4 pi epsilon naught r cubed. Okay. And we know that the force is Q times E. So it's going to be Q, and it's negative. So minus Q X divided by 4 pi epsilon naught R cubed. So we established that the electric field is that, and the force is the charge times the electric field. I hope you understand that. Just like force is gravitational field times mass, the same, the electric is the electric field times Q. Right? Gravitational field times mass, force is electric field times Q. That's a very important formula. So you have this, and we know that force is mass times acceleration. So mass acceleration is minus QX over 4 pi epsilon naught R cubed. Interesting. So acceleration is minus QQ over 4 pi epsilon naught R cubed M multiplied by X. And this is a differential equation because acceleration is X double dot. So X double dot, and we compare this, to X double dot equals minus omega squared X. And we see that omega is omega squared is Q over 4 pi epsilon naught R cubed M. Yeah. And the solution that X, well, if we drop it from the top, so it's going to be radius multiplied by minus R cos omega t, where omega is this one. So it's a some simple harmonic motion. So X is going to start with minus R, the way we defined it. It's going to go like this. T. So the mass would go bounce, 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 bounce. So that electric field Hawking. Let's see if we can simulate that. Wonder if this can be useful. No, this won't be useful. This would. Okay, so this is a positive charge. Let's put a negative charge and see. Something like that. The question is this simple harmonic motion? Have a think about it. Is this simple harmonic motion? Can you explain? Samuel? Acceleration always pulls towards the center. Yes, that's one of the things. There's a fixed amplitude. What is the other condition? What is the other condition for simple harmonic motion? Acceleration is negative, yes. Acceleration is opposite, is proportional to distance. Is it? You can actually see the force changing. Is it proportional to the distance? Yes, this is not simple harmonic motion. It does look like simple harmonic motion, but certainly is not, because actually as you go further away, the acceleration decreases. Now in simple harmonic motion, it increases. So yeah, be careful. This can catch you out. And now in this, so this is not the same scenario as we had, because we had a uniformly charged ball and we were inside. Remember, inside it's this. Inside it's simple harmonic motion. Outside, no, not simple harmonic motion. So inside SHM, but if we were outside, it's not SHM. It's HM. Right, so I did manage to catch you out, but yes. Here we are inside. I wonder if we can simulate a sphere. Probably not. Like, I would be really surprised if we could. Oh, no, we have to be like this. Missing. It's going to be a disaster, but let's see. So I've tried to recreate that we are inside a charged sphere. Well, something that might resemble simple harmonic motion. But yeah, very unstable, as I thought it would be. Yeah, but this is more like the situation. Of course, this is not. This is unstable. Okay, that's probably it for today. Do you have any questions? This is the last webinar, as I have already mentioned. If not, I will start. I will try to start in September. So hopefully by the second week of September, we'd start. What do we need to do to get letters of completion? Well, we just need to ask for one. Yes, so just email me and I will send you a letter. We might be able to do like automatic letters, but yeah, at the moment we just do them by hand for now. Oh no, we will do automatic letters. We will, yes, but you can ask for a personalized one. Don't advertise it. So it's a lot of work doing these letters, but we're happy to do on request. So for those of you who attend webinars, definitely happy to do letters for you. Thank you, Edith. That's always great to hear. If you have some feedback that you'd so we're constantly updating our website. If you want some feedback to give for our website, we're happy to just write a testimonial, and please indicate that you're happy for us to put your name on the testimonial, and just yeah, if you email us with the phrase testimonial and write something about us, and we will put that on our website. Where do we email? Vladimir.chernov at hey, what's going on? I will. Okay. Well done, everyone. Enjoy finishing the assignments and submitting them by the end of this week. And see you in September. Enjoy your summer. Welcome. You.